Okay. So today we're talking about, you can see the exciting title, probability mass functions. Okay, there we go. You can plot the probability of any given score for a variable. A variable is just a number that can take a different value, solid is, okay? So that's what x, with the quiz, for example. So you can plot the probability of any given score for a variable. It's an easy thing to do. The probability of all possible events is 1. Because probabilities can only go up to 1, can't they? You can't have more than a probability of 1. There are scores that have no probability whatsoever. 0, they can't happen. And then there are scores that, then there's the scores that are possible. All the possible scores, the probability of all possible scores is 1. Okay? The probability of flipping a coin and getting a head or a tail is 1. The probability of getting a chair when you flip a coin is 0. That's not even an answer, right? Probability of getting a head is 0.5, and probability of getting a tail is 0.5. Okay? Does that make sense? So one could plot such a thing. And in fact, the area underneath that curve, if you plotted the curve of all the possible events, equals 1. Okay? The area under the curve is going to equal 1. Questions so far? You with me? You with me so far? Okay. So let's say we're rolling a die. The probability of any given die roll is 0.16, which is 1.167, 1666666, repeated. If you take 6, because there's 6 possible rolls, and you multiply it times 0.167, you get 1. The area under those points would be 1. Okay? So the area then underneath, you add all these on. If we put all these on top of each other, it would go up to 1. Okay? Not too scary yet? You still with me? Okay, good. Now, we don't often plot things about die rolls because it's uninteresting and they're all the same. The probability is pretty easy. However, we use this quite a bit, the normal distribution. Right? This is our old friend. Hello, normal distribution, my old friend. Has some properties that we know about. It has a mean of mu, a standard deviation of sigma. We can go plus or minus 1 standard deviation, plus or minus 2 standard deviations. The area to the right of the mean is 0.5. The area to the left of the mean is 0.5. 0.5 to 0.5 is 1. This isn't magic. This is a property of the universe. Okay? This is a thing. So the area underneath that whole thing is 1. So let's move this over a bit. It's the most common distribution, at least it's the most useful to us. When we're going to do inferential statistics, the most useful distribution we have is the normal distribution. It has a few characteristics that are important that I think you guys know about. It's unimodal. It has one mode right here. And then it's nice. It's unimodal and it's symmetrical, which usually means the mean equals the median equals the mode, and that's what's happened. Okay, the most common value is the mean. It's also the 50th percentile. It's also the mean. It's the balance. And it's, quote, bell-shaped. So you just talk about the shape. And if we're going to do anything with the distribution at all, we have to know the central tendency, we have to know the spread, we have to know the shape, and I just told you those things. Right? Questions so far? This is something I'm sure you've seen before, but again, I know for some of you it was a very long time. Okay, good. So you're okay. You're still okay. Okay, good. So one might ask, why is that useful? Well, many variables are assumed to be normal in the population. They may actually not be. You're told in intro stats, in stat 2126, for example, you're told that in questions that are developed by either people that are teaching it or by textbook authors for assignments. You're told things like the average life of a light bulb is normally distributed. It's a crock of shit, actually. You wouldn't want, a company wouldn't want normally distributed because you'd have bulbs that now and then get plugged in and they just snap. You don't want that. They're actually skewed all to hell, those distributions. But it makes a nice story. Human height, however, especially within the sexes, is normally distributed. That's a good example in the population. IQ is normally distributed. You might say, well, yeah, but it's designed that way. Yeah. We make the tests that are normally distributed with a mean of 100 and a standard deviation of 15. It's built that way. It's probably the case that most personality sort of psychological variables are like that. Okay. So a lot of things are either assumed to be normal or actually are normal. And there are all kinds of things, those of you guys that took learning with me know that a generalization gradient for an animal, generalizing about a stimulus is a normal distribution. A timing distribution, if animals keep track of time, is normal. That includes you, by the way, because you're an animal. So we can use, this allows us to use certain standard techniques, which is what this whole course is about, is these different techniques one can use to do inferential statistics. Now, sampling distributions are normal. That's by the central limit theorem. A sampling distribution is just all the possible values a statistic can take. The probability of all the possible values a statistic can take, and then just the distribution. That's a sampling distribution. And sampling distributions of the mean, all the possible values a mean can take, are normal. They just are. It's great, it's crazy, the world just works that way. There's all kinds of really neat math behind it that shows that it's true, by the way. This isn't just something somebody guessed and made up. It's a real thing. We'll talk more about the central limit theorem as time goes by, but the point is that sampling distribution of mean is normally distributed. So many sampling distributions are, especially the one we're going to care most about, which is the sampling distribution of the mean. All the possible values, the distribution of all the possible values the mean can take. I mean, that sounds kind of weird. So what we do, let's say we're doing height in this classroom, and this is the population in this classroom. And we're going to measure, we're going to randomly select 4 people, and we're going to measure their height. And we're going to average it, and then that's one data point. Then we're going to do another set of 4, and we're going to get their average, and we're going to plot that. And another set of 4, and we're going to average it, and we're going to plot that. Eventually, we get all the values the mean can take. It is kind of weird that you're plotting values the mean can take, but the numbers don't know where they come from. They don't care. Right? So you actually get a normal distribution. It's crazy. It's weird. It even works with flipping a coin. Coin flips, there's 2 possible values, 1 and 0. Well, what do you mean? Well, we're going to say number of heads we get, because we can't put a value on head or a value on tail. And we're going to flip the coin 10 times. Most likely we're going to get what? 5. That's just intuitively pleasing, isn't it? But sometimes you'll get 6 heads, and sometimes you'll get 4 heads. So let me draw this up. So we're going to flip a coin 10 times. And we're going to plot up the number of heads. The most, I think we all agree, the most common roll we're going to get, or not roll, but flip we're going to get is 5, right? Like 5, when we do 10 times, we get 5 heads, most common. Sure. But sometimes we're going to get 4. And it actually, probably the same number of times, we're going to get 6. And if we look at, say, 7 and 3, that happens. That's going to be pretty rare, isn't it? It will happen, but it's going to be rare. Much rarer than getting 4 or 6. So maybe right around here. And then 2 and 8. That's getting really unlikely. And then just 1 head or 9 heads. Pretty unlikely. 10 heads, it's going to happen, but it's going to be vanishingly small that it happens. Or 0 heads. It's going to happen. And, oh, look what happened. Magic. By the way, you can do this yourself. If you've got a lot of free time, and I know most undergraduate students have tons of free time, what with not having to work to pay their tuition and only taking 5 classes. Joke. But you can get out a die or a coin. Do this flip a coin, flip it 10 times, do that maybe 30 times. Again, so that's 300 coin flips. Plot it out. You'll be amazed at this beautiful normal distribution you'll get. It's really cool. It's really quite neat. It won't be perfect, but if you'll look at it and go, after about doing it maybe 10 times, you'll look at it and go, wow, that's really approximately normal. The parent population distribution is binary, 0 and 1, yet we get that. Isn't that neat? Now there is math behind this that proves it, and we don't have to go into it. But there is proper math that does this. Okay. Questions about that? So that's a sampling distribution of the mean of the number of 10 coin flips. That's what that just was. The central limit theorem is the thing that tells us this. In fact, the central limit theorem tells us that the sampling distribution of the mean is normal with a mean of mu sub x, that's just the mean, and a variance of sigma divided by the square root of n, the number of, in our case, coin flips. That's not too scary. So it just says that we're going to get, it's normal, that's what the n means. It's got a mean of x, mu sub x, which is just the mean, and a standard deviation of sigma divided by the square root of n. Okay. So we can demonstrate it pretty quickly by doing this, doing our pretend coin flips. That's intuitive. This might not be. But what would the variance be, or the standard deviation be, if we're not going to go with coin flips now, because that counts on a population with an infinite number of coin flips. That's no good. You can't imagine that. But we have, 2, 4, 8, 9, 10, 11, 12, 13, 14, 13, 17, 21, 23 people in here tonight. 24, blue beam. And we're going to take let's say if we randomly selected 5 people and did their heights, we'd again, I think you'd agree, we'd get something like this if we plotted it up. But I would have a variance, a standard deviation of some sort. What would happen if we selected, instead of 5 people, 15 people? It'd get a little tighter. What if we selected all 24 people every time? This is a sort of stupid example, but it makes some sense. What variance would we get, assuming we have a really good pigment? We'd get no variance, wouldn't we? Because we'd always get the same damn number. Right? We'd always have the same number. So in other words, the bigger n gets, the smaller the variance gets for a sampling distribution. Right? And the mathematically inclined among you, think about this. The limit as n approaches infinity of sigma squared over n, or sigma over n, equals 0. If that didn't help you at all, don't worry about it. But if that's something you still learn limits in school, right? But the looks on your faces, they don't teach you anything anymore, do they? Just like Harry Potter, that's all they teach you. It's like pretend spells, stuff like that. That's all they teach you, right? So, if that helped, all that says is, if this thing becomes infinitely large, if the sample's infinitely large, the variance is 0, isn't it? Because a number divided by an infinitely large number is nothing. It's 0. Okay? That's all that limit thing means. Do they really not teach limits anymore in school? So who learned about limits? Don't matter if you remember. Oh, good, you did learn it. Okay, so some of you. There's hope yet for the future. And you all sat there in class going, I'm never going to use this again. Well, here you go. So maybe it helped you. If it doesn't, that's okay. Just remember, the bigger that number gets, the bigger the sample gets, the smaller the variance gets. Okay? So that's interesting because we're going to care a lot about this distribution, the sampling distribution, the mean, because it's normal, so we should know a lot about the normal distribution. Okay. Question. Okay, let's look at this is a weird part of the distribution. This is the little known triangular distribution. I've never seen it. But what we have on the bottom are just values. right? On the x-axis are values. And on the y-axis, this will be probability. Okay? So it's the probability of getting any of these scores. You okay? You got that? Make sense? All right. So if we wanted to find the probability of getting a score between 3 and 7, which is a question one could ask, we would just look at the area between f at 3. Oh my God, remember that? Functions? Haha. F at 3 and f at 7. In other words, between here and here, what's this area? We could do that. That's a thing we could do. It wouldn't be that hard. Okay. Do you understand the logic of that? You see what I'm saying? Does that make sense? Okay. So it's just the area under a curve. This is all about the area under a curve. And in fact, that case, it's pretty easy. It's just geometry. You've got a square, or a rectangle or something, doesn't matter which, and a triangle on top of it. I know you were taught the formulas for how to get the area of a rectangle and how to get the area of a triangle. You may not remember them. Length times width into the rectangle, and half base times height. Remember that? Mm-hmm. Okay. Doesn't matter if you remember that. This is the last bit of geometry we're going to do with the whole course. But one could do that. One could do that if it's a common shape. But the normal distribution, while it's all over nature, and this weird thing in the central limit there, it doesn't look like a shape I ever learned anything about in elementary school about how to find the area of. No one taught me that. No one taught me that. Anybody here taking calculus? Nice. How do you find the area under a curve? Take the integral. Now, if you don't know what that means, don't worry. All that says is we're going to find the integral, which is an equation that tells us the area under a curve, and find the values between 3 and 7. In fact, it's exactly what I said between f at 3 and f at 7. That's all that is. That's all that is. Okay? Don't get frightened. You're never going to have to do any calculus. You should have done some calculus. You were poorly advised in high school. Calculus is neat. It's such neat math. It's math that describes the universe, which is really, really cool. And it's one of those, there are moments when you take calculus, when you find out how a derivative works and to find the slope of it's so neat. But it's too bad that you didn't do it, so a lot of you, most of you. Again, I don't know what's going on anymore. It's sad. Because it is so neat. But one could do this. Many of you couldn't, but that's okay. It's too bad that people don't take calculus. But don't worry, you're not going to have to. But the point is, this is all based on real math. It's not, I know in 2126, in intro stats, it seems like at times you follow it, and then it's just magic. Right? So when this happens, I do a t-test. Why? Because Dwayne said so. No other reason. Right? It's just, that's how it works. I don't know why you're all talking with that ridiculous voice. I know what that was. That's my dumb guy. I mean, I was thought stats that way too. But in fact, there's really beautiful math behind all this that we're not going to worry a great deal about. Don't worry. And for those who go to graduate school, you likely won't even worry about the beautiful math behind this in graduate school. You'll probably be shown it and then told. Remember when I was in grad school, we were told, "Here's the proof of the central limit theorem." Well, you're never going to have to memorize this. It's ridiculous to look. It's a tool. We're using statistics as a tool. This isn't a statistics class, right? But it is neat that there actually is math behind it. So, wow. Remember, we'd have to know, we have to know the formula, and if those of you who have taken the calculus, you have to know the formula to take the integral. That's actually the formula for the normal distribution. F of x, or y, equals 1 over sigma times the square root of 2 pi times e to the negative x minus mu divided by 2 times the variance. Wow! So one would have to take the integral of that. How recently have you guys taken calculus? Out of curiosity, you guys have taken calculus?
3 years.
3, 4. Looking at that, that's an evil-looking integral to take, isn't it? It's hard. You got an exponent, negative exponent actually. It's that. That's hard. Oh, e. Do you know what e is? E is the natural base of the natural logarithm. It's a mathematical constant. It's like pi, except it's not pi. It's e. Okay. It's 2.71828 something else. Yeah, go ahead.
Who all comes up with this?
What do you mean, who comes up with it? Nature. The universe. This is a property of the universe.
Yeah, but it wasn't just written on a rock.
Who figured that out?
Yeah.
That that's the formula? A guy named Baron von Gauss.
Do you have a wife?
Yes. He was yeah. And he actually figured this out when he was about 14. He figured this out when he was 14, so I think he was married then. Oh, and the calculus, that was invented by a guy named Isaac Newton. And Leibniz. They probably both invented. They discovered. You don't really invent math, you discover math. Because it's a property of the universe.
And I'm guessing it's before Pokemon, so hence why he had enough time to do this.
Yes, it was pre-Pokemon. Yes, it probably was.
You sure?
Yeah. You got to catch them all! It's a German guy. 1640. So the neat thing about this is, and you have to keep this in mind, that the normal distribution, see, what we're putting here? We're putting in the variance, and standard deviation and variance here. We're putting in the mean. And then we'll just have a couple of mathematical constants. Okay, so it's actually pretty cool. So you just take the integral of that function. As I said, that's hard. That's a really evil integral to take. It's hard to do. One could do it, but it would be very, very difficult. I did pretty well in calculus. I got 100 in calculus in high school, and I got 80 in university because I stopped understanding it sometime in March, and I stopped just going to class. So I was wasting my time and the prof's time. God, he was a neat guy. Dr. Kochman. He was an Orthodox Jewish guy, and he worked. So he yawned every day, he had a prayer shawl on, and he was just cool. He was he looked like every university math professor looks like in a movie. And I remember him, there was 200 people in the class, and he knew all of our names, which was really cool. And he called us Mr. and Miss, which was really cool, because it was like, I'm in university. This is what I've seen on TV. And he's up with this great big gray beard. And we were doing Clarence series, which I just didn't understand. And he said, I guess it was called. And I got up to leave. And he said, Mr. Ryback, where are you going? And I said, sir, I'm sorry, I don't understand this. I really tried. And I'm wasting your time, and you're wasting my time. I'm going to the Spoke, which is one of the student pubs in Western. He said, well, good luck. He was so cool. He was so cool. And that's when I stopped understanding. I understand enough calculus, I understand it conceptually, but I can't really do it very well past the sort of middle of first year. Mr. Captain Doctor Smart Guy up here decided, see, at Western you have to do stats in psych, you have to take a first year math, 6 credits of first year math. So they have math for social science majors, which is basically, I believe, pluses and minuses. I took math for math majors because I'm an idiot. It'll be more of a challenge. I don't know what's wrong with me sometimes. So, let's say we want to find the probability of getting an IQ between 95 and 107. Okay? Of randomly selecting a person in a population of humans that has an IQ between 95 and 107. All you do, it's actually pretty easy, is do the integral of this. You put it, well, let's see. That's going to be 15. That's 100. That's 225. That's a little bit easier. But you know this. You've seen questions like this. Did you do any calculus when you looked these things up? No. somebody did calculus for you. So we could make this a lot easier. What if we made the mean 0 and the variance 1? The equation gets a lot easier if the mean 0 and the variance is 1. Again, I'm never going to ask you to write down this equation. I don't care that you memorize such a thing. If you want to, feel free. But that's a little bit easier if you don't know how to do calculus. That's still a hard integral to do, but it's a little bit easier. We put the mean 0 and the variance of 1. Suddenly things get a lot easier. It's still a pain. If we make the mean 0 and the variance 1, we have what's called a standard normal distribution or a Z distribution. Or if you're American, a Z distribution. The same Z is too hard or something. I don't understand. The rest of the world we say Z. All right. So that makes it a little bit easier. But again, it still means you have to know how to do calculus, and that's still a really nasty integral to take. So still, what we do then, we do something like this. We're going to convert 95 into a z-score, negative 0.32. We're going to convert 107 into a z-score, 0.466. And then we're going to look up in a z table what's the probability of getting a z value between negative 0.32 and positive 0.466. Probably your z table doesn't do that. You probably need to get something like between negative 0.32 and 0.5, and then 0.5 and 0.466 and add them together. You've done these things before. So basically, that's why we standardize our numbers, the z distribution, to make it normal with a mean of 0 and a standard deviation of 1. And that's because that area under that curve, the calculus to do that has been done already. Some poor graduate student back in the 1800s or early 1900s did it for you and wrote it down. Every time you do anything when you look it up in a table, just say a little nod to the poor bugger whose job it was to do that integral over and over and over. Right? So you know how to do this kind of thing. And it's actually not that difficult. It's because someone did the calculus for you. So you look it up in a Z table. There's actually a web tool here, and so I've got a link there, but I've also got, there's the actual URL. This is a really useful website, because in fact you can just put in the values, and it'll give you the probability. And there's all kinds of, and I believe it runs on Java. It's really, really simple. So check out that. He's got quite a few nice little web tools on his webpage. He's a stats prof. I forget what the hell he is, but he's got some really nice stuff there. So in fact, if you look it up, this is what you end up with your input and your output on that at that website. Mean of 0, standard deviation of 1, because we converted it into Zs, right? Between negative 0.32 and positive 0.466, and the value is right there. It just spits it out for you. It just spits it out. It's beautiful. It's actually a really useful website for doing things like separate normal distributions. Really easy to use. Really easy to use. Okay, questions so far? Because we're almost done this, but I want to see if you have any questions, because I know this is the first stuff that was probably, that involved thinking. The rest involved remembering stuff about, oh yeah, mean. Oh yeah, standard deviation. This is the first time you've had to probably think a little bit. Yeah.
When you're talking about the properties between 3 and to find the
probability between 3 and 7, yeah.
So what would you really be finding? Like an actual
Finding the area under that curve. It's the probability of getting a score between 3 and 7. Yeah. So someone getting a score. Notice that it says less than and greater than. It doesn't say actually less than or equal to. You can never find the probability of getting an actual score because it's a continuous variable. That's just something new. P is never equal to anything, for example. It's always less than something because it's a continuous variable. And because it can take an infinite number of values. That's just an aside. All you're doing here is you find the probability of getting a score between, in that case, 3 and 7.
And it could be any numbers of
Could be any set of numbers, doesn't matter, as long as they're in the distribution. And to do that, what you're doing what you're doing if you have a probability mass function in front of you is you're taking the area under the curve between those 2 points. That's all you're doing. And the total area under this curve is 1, just like it is under any other probability function. Check.
So why is the probability over here 0.310 and over here 0.304?
It could be that I rounded incorrectly
Okay.
when I did it myself. That's why it is. Yep. This is pretty trustworthy, this thing. Other questions? So far, I want to make sure you understand what's going on here. All you're ever doing when you're doing these Z calculations, and in fact later when we do, say with t-tests and plate analysis variance, all you're doing is looking at areas under curves. It's really all you're doing at a deep level. This is why this works. This is why we can make these statements like the probability of getting a score like that is less than 0.05. We can make that statement because it's a property of the universe. The world works this way. And someone did some calculus for us, more than someone. Many people did calculus for us. Before these tables existed, before Z tables existed, for example, you had to do the integral yourself. Okay? A long time ago. Okay. Some conclusions about this. First thing is, some poor person did the calculus for you, and you should just, like I said, always keep that in mind because someone did this, and they're a nameless, faceless person in history. Some poor graduate student sat down with a piece of paper and gaslight and a fountain pen and did this. Or perhaps a candle. Could be a candle. Probably wearing an academic gown or something. We look it up at a table, or like use that web tool that I showed you. But you can do this. You have done this before with a table. It's not hard to do. One can do it. Okay. This isn't that scary. It may seem, I've presented it differently than the way it was presented to you when you were mere children last year. It was presented to you differently, and it's funny, it's one of those things where you think, why don't they tell us the math behind this first, rather than say, this is how you do it and it's magic. Right? Well, the reason is that when you're going to use this as a tool, you have to just know how to use it first. When you first learn to cook, and people call those kind of courses cookbook statistics, right? When you first learn to cook, you read directions. You read recipes, and you read them slavishly, right? I don't have any beef. Can I use lamb? No, you will die. Of course you can. Of course you can. Can I cut that in the salt? No, it would stock me in bread. It would become a cake. No, that doesn't happen. But some people are afraid of cooking, and they just follow things very closely. You have to do that first. Eventually, you learn how to cook, and you learn how cooking works, and you know that you can play around with ingredients. It's the same sort of thing here. You're going to learn in this course how to play with statistics a little bit. And how it works, the other reason, frankly, is because if we started out the intro stats course, the one that every psychology student, every biology student, and all honors geography students have to take, if we started it out like I started today, half the class would drop the course. Right? Because people are frightened of numbers. They think statistics is math. It's not. The beautiful thing about it is there's really cool math behind it. So any other questions? You're going to be okay. Okay, I know I filled your brain a lot today, so we're going to stop now because we're done. And I'll see you next time. Thanks, guys.